This is the second class of this week. As you remember, last class we discussed there are three important ingredients of equations for elasticity. One is equilibrium, which tells us how the stresses are related to different component of stresses are related to each other, and then we have compatibility or strain compatibility, which tells us how the different components of strains are related to each other, and then third one, which is the relation between stress and strain, which is the constitutive relation. Now today we will start equilibrium equation. Okay. Now, so before we do that, let us since equilibrium equation is essentially tells us the summation of forces is equal to 0 in a particular direction. One important thing, whenever we say equilibrium, by implicitly it is implied that we are talking about static equilibrium. Okay. Now, so static equilibrium is what? The summation of forces in all direction is 0. Summation of moment in all direction, summation of moments about any point is also 0, but the symmetry in the Cauchy stress tensor automatically satisfy that moment balance equation. Now, since we have to at the end we have to write the equation in terms of stresses, but the equilibrium equilibrium is always equilibrium of forces. Equilibrium, there is nothing like equilibrium of stresses. Okay. So, essentially you have to start deriving the equilibrium equation in terms of forces. Let us understand what are the different kinds of forces that a body can have. Now, the first thing is the body force. Body force is, for instance, gravity is a body force, then the magnetic forces, electric forces, they are the body forces. What is that? The body force is defined, it acts over the entire body, and it is defined by, suppose, a function say Bx. For instance, if it is gravity, then it becomes the density, how the density is distributed among the body. So, if the body force density is Bx for a given arbitrary three-dimensional object with volume V and the surface is S, volume V and the surface is S. The boundary of this object is represented by S. Okay. And Bx is the body force density. It could be density, it could be the body force density for magnetic fields, electric forces. So, it depends on which kind of analysis you are doing. Depending on that, the Bx will be different. So, if Bx is the density of the body force, then it has to be integrated over the entire volume to get the total body force on the system. Okay. Now, in this course, possibly in this course we will be only dealing with this body force, gravity, the self weight of any object. Okay. Now, so this, in addition to that, there is one more force that we can have is the surface force. Surface force is, if you recall in the previous class, when we talk about what are the conditions, boundary conditions specified at the surfaces, we discussed that the surface and those are the surface forces, that is represented by on any surface the stresses represented by traction at any point. Now, suppose T and x is the Tnx is a function which gives you how the traction, it is essentially the surface force density, how it is distributed over the entire surface. Okay. Now, if we integrate it over the entire surface S, then we get the total surface force. Okay. Now, these are the two important forces that a body can have. We have the body force, which is the gravity is a body force, and then we have a surface force, the forces acting on the surface of any arbitrary volume. Now, once we have these two kind of forces, let us see how to derive the equilibrium equation for elasticity. Now, take arbitrary. There are two approaches. One approach that we are going to do here, which is very general, and another approach is that is also available in any book, where you take an infinitesimal volume element as we discussed, by representing the stresses, write the stresses on different planes, and then convert the stresses into forces, and then write the equilibrium of that forces. That is another approach. This approach is again similar to that, but it has been written in a very general form. Now, suppose we have a three-dimensional object like this, then we take a very small volume element into this object, an infinitesimal volume element into this in this object. Okay. And let us draw the free body diagram of this object. Okay. Now, what are the things we can have on this object? We can, if this three-dimensional body has a body force distributed over the entire body, then this small chunk of continuum, this is suppose this volume is V and again the surface is defined by S, then this small chunk of continuum, the one force is the body force, and then since it is taken out from this entire three-dimensional entire object, then if I call that this is part number 1 and this is part number 2. If you recall, when we discussed traction, then we define traction is a field through which these two different parts will interact with each other. So, if we take this thing out from this object, then we will have traction on these surfaces. Okay. And through this traction, this small part, the part 2, will interact with part 1. Okay. Now, then we have, suppose the body force density is Bx, and then in addition to that we have a traction T and x. It is a function of x, means it is the traction may be different at different points. Okay. Because the state of stress is different at different points, and the plane also, the tangential plane is also different at different points. But for clarity, it is not shown over the entire surface, it is just shown, it is a representative traction shown on the surface. Now, so if we have that, so this is essentially the free body diagram of an arbitrary portion of the continuum. Okay. Now once you recall how you wrote the equilibrium equation in strength of material, when you draw the free body diagram in any object, then the equilibrium equation free body diagram is essentially what? We take the object from the entire system and write the forces acting on the object, and then write the equilibrium equation on that free body diagram. Writing equilibrium equation means writing the forces adding the forces in different directions in a particular directions, and then equating them to 0. So, what are the forces then we have here? We have, if we integrate these body force over the entire volume, then we have body force. This is the total body force on this small chunk of continuum, whose free body diagram is shown here. And then we have surface force, which is the integration of Tn. Tn is the surface force density. So, these two forces we have. Now, please note, these forces are written in vector form. Okay. Now, the equilibrium says then these two vector, the forces written in a vector form, the addition of these two forces, the total forces, has to be equal to 0. So, the equilibrium equation says that that summation of F, the summation of body force and the summation of surface force, that has to be equal to 0. There is no inertia here, because we are talking about only static problem. Okay. So, this is the equilibrium equation. Now, let us see what this equilibrium equation let us now, this equilibrium equation is written in terms of forces. Now, let us see how to write the same equilibrium equation in terms of stresses. Okay. Now, so once we have this, then you see, so F is directly from here we can substitute F and Fs here. So, we have this expression. It is not shown here properly, but you please note that this integration is over surface, and this integration is over volume. This is very important. Okay. Now, so let us see next. So, this is the equation we have. So, this is total equation we have. Now, you recall what we have. You recall Cauchy stress tensor. If we have any arbitrary plane, if any arbitrary point in any three-dimensional object, and on that point if we construct a plane, and suppose this is your actual object, this is the actual object, then we have traction on this plane, this is the traction on this plane. Okay. And this traction can be represented, and then the sigma is the state of stress at that point, and n is the normal to this, n is the normal direction, n is the normal which defines the plane. So, traction vector can be obtained as sigma dot n. Is the projection of sigma, the stress. So, on this surface we have several points. So, at every point we project that stress onto a plane which is tangential to that surface, or the plane which is defined by the normal vector n, then we get traction. So, essentially T n gives you this. Okay. Now, if we have this, then substitute this T n here, and we have this. Now, another important theorem that we have discussed in the very first week, that is Gauss theorem, divergence theorem, and what it says, it essentially tells you how the surface integral of any object, surface integral can be projected onto volume integral, or the volume integral can be projected onto the surface integral, like this. Okay. So, now if we have, if for any variable, any field variable, say u, and if at any point if n is the outward is a normal vector, then the integration over the surface can be converted to volume integration like this, when del is the differential operator. Okay. Del, you remember, del is del del x, del del y, del del z. Okay. Now, if we substitute this, from T n from this, and then again this surface integral, if we convert it to volume integral, then what we get is, we eventually get it this. Okay. So, now this is also integration over volume, this is also integration over volume. Now, let us combine them together. If we combine them together, then what we have is this. If we combine them together, what we have is this. Okay. Now, this is important. Now, you see, this is true for when we took this chunk of continuum from the entire domain, we did not have any specific assumption. We have just taken arbitrary manner. Okay. This is an arbitrary portion. This is very important word, this arbitrary portion. So, this is arbitrary. So, this equation is valid for any part. For if any part you take, any chunk of any portion you take from the entire domain, this equation is valid. And if it is so, then this is only possible if this integration of something over dv, and that dv, that over this domain is arbitrary, and that is taken that can be taken anything, then we can have is this integrand has to be equal to 0. The integrand has to be equal to 0. This is only possible, this integrand has to be equal to 0. Now, you see, you recall our equation was F plus Fs is equal to 0. It was body force, and this was surface force, and this equilibrium equation is now written in terms of stresses. Okay. Now, so if I write this equilibrium equation in initial form, this is the divergence of sigma, and you recall in the very first week we discussed how to write the divergence, what is divergence of a tensor, first order tensor or second order tensor. Divergence of a second order tensor can be written as in this way, and then the B is a body force, and the body force can have density, say B as a vector can have, say, Bx, By and Bz direction. Okay. So, Bx is the body force density in x direction, By is the body force density y, and it is z direction. Suppose if you are taking gravity and which is acting only downward, then we can have something like this, which is 0, minus g and 0 and so on. Okay. So, this is the equilibrium equation written in terms of stresses and written in initial form. Okay. Now, next is, so if I expand this equilibrium equation, it is written in initial form. If I expand it, if I write I j in terms of x, y, z and so on. So, these are the three equations we get. This is equation number 1, equation number 2 and equation number 3. So, this is equation essentially what equations we have. The equilibrium equation is a summation of force in x direction is equal to 0, and then summation of force in y direction is equal to 0 and summation of force in z direction is equal to 0. So, essentially it is same, but now in strength of material you use this equation, all these equation you use equilibrium equation, it is same equilibrium equation, but now written in terms of stresses. Okay. So, already you know this equilibrium equation. So, this is the 3 equilibrium equations we have, and this equilibrium equation is with respect to Cartesian coordinate system. Okay. Now, let us write the same equation with respect to cylindrical coordinate system. Now, cylindrical coordinate system, the stress is defined as this. We have 3 axes. One is r. One is this axis r. These r, and then we have theta. This is theta, and then we have z. Okay, and suppose E r, E theta, and E z are the corresponding basis vector in r, theta, and z direction. Okay. What are the stress component we have? Now, suppose this plane, if we take, this plane is normal to the r direction. Okay. Now, we have 3 stresses on this plane, one is normal stress and 2 are the shear stresses. Now, normal stress is represented as sigma r r, because it is acting on a plane normal to the r, and the stress direction of the stress is also in r direction. This is sigma r theta, and which is acting on a plane which is normal to r, that is why the first r, and the second is it is acting in the direction of theta, that is why second theta. And then this is sigma r z, it is acting on a plane normal to r and in the direction of z, that is why it is r z. Similarly, if you look at the other plane also, we have 3 stresses, and then 3 stresses are the representation of these stresses, we follow the same approach. Okay. Now, if we have this, now this same sigma, if you recall that the stress any second order tensor can be represented by in initial form as this. These EI and EZ are the basis vector in r, theta, and z direction, and sigma ij is the component of this. Okay. And if it is, this is a tensor product. So, tensor product between 2 first order tensor, I and j are the basis vector, they are first order tensor. The tensor product between 2 first order tensor gives you second order tensor. Okay. So, sometime we do not have to write this explicitly, the tensor product. If you write EIEJ, it automatically means it is tensor product. So, essentially it is a it is the same matrix, same second order tensor written in initial form. Now, so another thing we know that, suppose this is a plane. Okay. Now, this is a plane. On this plane, we can have a traction like this. Suppose that traction is T r. Okay. Then similarly, on this plane we can have traction like this. This is T z, and on this plane we can have traction like this, and suppose this is T theta. Okay. Now, T r, what are the stresses we have on this plane? We have sigma r r, sigma r theta, and sigma r z, and E r, E theta, E z are the basis vector is r theta z coordinate. Then T r can be represented as this. Okay. Similarly, T theta is also can be represented as this, and T r z also represented as this. Just one thing, please note, you recall when we discussed traction, when we defined traction, we used a notation something like this, T n. Okay. T n means this is a traction on a plane normal to which is defined by a normal vector n. Similarly, T e I is a traction on a plane which is defined by normal, which is defined by the basis vector E I. So, T r is essentially this is essentially T e r. Okay. This is essentially T e theta, and this is essentially T e z. Just to avoid this again and again, it is written as T r, T theta, T z. Do not get confused with the notations. Okay. Now, so these are the traction on different planes that can be represented at this, and if we have this, then sigma, this sigma can be represented as this traction. Okay, the traction. Okay. Now, once we have that, So, we have sigma represented in terms of traction on different planes like this. Okay. Now, each individual, say T r, T theta, T z, that each individual they are first order tensor and sigma is a second order tensor. Okay. So, they are not scalars, please remember it. Not now. Next, once we have that, suppose B is written in terms of in r theta z direction is BR, B theta and BZ, the way we wrote Bx, By, Bz in Cartesian coordinate system. And then we have equilibrium equation is this, which is a general. When we derive this equilibrium equation, we did not have any specific coordinate system. This equation is whether you use a Cartesian coordinate system, polar coordinate system, spherical coordinate system, cylindrical coordinate system, many coordinate system you use these equations will remain same. Okay. Now, but the representation of sigma and B and del operator, the divergence operator, they are different in different coordinate system, and when we replace that representation in this equation, we get the equation with respect to different coordinate system, and that is what we are going to do right now. Okay. Now, so you recall in polar in cylindrical coordinate system, if we have any vector, any first order tensor u, which has component u is equal to say u r, u theta and u z, then in cylindrical coordinate system the divergence operator takes this form. In Cartesian coordinate system, what you get it? Okay. Now, this is the operator. Now, next is we substitute. We have in this expression what we have? We have expression for B. This is the expression of a B. We have expression for sigma, this where T r, T theta, T z are expressed like this, and then we also have, we also know that if any first order tensor u, the divergence of that in cylindrical coordinate system, it can be written like this. Now, next what we do is we substitute this, all this B del u and this thing into this equation. If we substitute that, then what we get is we get this equation. So, this equation is the same equation that the equilibrium equation written in cylindrical coordinate system. Now, if you are polar coordinate system, then the z axis if z axis will vanish, then we'll have just two equations, one is in r and one is theta direction, and all the term associated with z they vanish. Similar way you can write the equilibrium expression with respect to in spherical coordinate system. Only thing what we have to do is we have to start with this definition, and then write del, sigma and B in terms of particular coordinate system, and then when we replace that coordinate system representation in this equation, we get the equilibrium equation with respect to that coordinate system. Now, you do not take this the final expression for granted, you must derive this equation, and the derivation is very straightforward. You have to just replace them, and then you see what becomes dot product of r theta, e r e theta, dot product of e theta and so on, and you get the final expression, all this. Not only in this class, in many classes we will see many things we may not derive explicitly. We discuss how to derive something, and then we give you the final derivation. So, please do not take that final derivation for granted. You must derive all this, everything that we discuss here, you must derive on your own, then only things will become clear. Okay. Now, you see, so this is equilibrium equation. As we discussed, as we started our lecture, there are three important ingredients: equilibrium equation, compatibility and the stress strain relation, the constitutive relation. Today we discuss equilibrium equation. Next class we will see what is will derive strain compatibility equation. But before that, there is one very important very important observation. You see, this is the equation that we have in cylindrical in Cartesian coordinate system, and we have only 3 equations, right? We have 3 equilibrium equations. Okay. Now, let us see how many unknowns we have. We have sigma x is unknown, sigma yx unknown, and then sigma zx unknown, sigma yy unknown, sigma zy unknown, and sigma zz unknown. These are not unknown because sigma yx and sigma xy are same. So, essentially we have equations, we have 3, and unknown we have 6, right. If you need 2 dimension, then also we will see that your equation will be having you have 2 equations. You will be having 2 equations in 2 dimension, and the number of unknown will be 3, sigma xx, sigma x, sigma yy, and sigma xy. Now, so we have less number of unknown. Recall in strength of material, when you analyze some structure, you applied the equilibrium condition and you found that you have the equilibrium equation not enough to analyze the problem completely, then we had another set of equation. We derive another set of equation based on displacement compatibility, and that is the compatibility equation here, the same compatibility equation, but written in terms of strain. That is why it is strain compatibility relation. Even in polar coordinate system, if you check that your unknowns are, you have 6 unknown, and then your number of equations are 3. So, next class we will discuss what is compatibility, what the compatibility physically mean, and then how that compatibility between different parts of a continuum can be ensured. And when we translate, then when you write that compatibility equation in terms of mathematical equation, what is that equation, what form that equation takes. Okay, then we stop here today. See you in the next class. Thank you.